Uh, no promises. Honestly, no promises. So, okay, let's boogie. All right. Hello, y'all. I'm Andrew Myers. I'm an inventor, a problem solver, an advocate for others, a Christian, a soon-to-be husband, and a guy with a big brain and an even bigger heart. And the Dalai Lama said that, so you know it's true. So my theme is assistive medical devices used to augment disabled individuals' abilities. So that really revolves around kind of adding something into the system so these people that can't do something can do it. And that is that can be done in a million different ways. So really, I want to talk about who I am as a person and why my theme kind of coexist and why that kind of works. So what really happens is my passion for medical devices is the intersection between my greatest desires and skills and the world's needs. This is where like all the parts of me that make me intersect, where my faith meets my engineering skills and my heart connects to my hands. So from like a really young age, I really realized that I had a passion for making things. And through the encouragement and learning from mentors and teachers and professors, I've honed tons and tons of different skills. But especially from entering into the Creative Technologies program, I've learned how to not only learn more skills, but learned how to apply these skills to a particular problem and apply them in such a way where I can solve problems, but also create lasting impact with those solutions. So the first of which of these solutions that have lasting impact, I kind of want to talk about the Equus Hand. So this kind of sprung from Dr. Grout putting me in contact with John Crowley, a prosthetist at Redmond. And he put me in contact with Libby Brewer and her family. So Libby is shown right here in the right picture you can see. So I met up with Libby. I saw her ride her horse and watched her and her sister actually ride side by side to see kind of the differences between someone with a limb deficiency like Libby, which just means that she was born without her arm and she actually ends right below the elbow, and her sister who is completely able, with no disabilities whatsoever. So the task was to develop an arm that will allow her to hold the reins of her horse so she can more safely maneuver the horse. But also it would be a huge plus if she could use this arm outside of that. So outside of the arena, off the horse, just in daily life using it. And the solution I came up with went through a ton of different iterations. First of all, I actually designed my own hand from scratch to start with, which wound up being too complicated for how little she was. So printing these parts was incredibly difficult for how small an arm she has. But wound up taking an existing design and then pretty much redesigning the entire thing to fit Libby personally. So I wound up adding notches to the hand, as you can see in the picture. I wound up adding different lengths to the bicep cuff and to the forearm cuff. And finally settled on printing the whole thing in PLA so that I could thermoform it. So I could heat it up in hot water with a hair dryer and form it perfectly to her bicep or to her forearm, her little nub, she likes to call it. So it would fit her perfectly. So that's kind of like solving that issue and how I found that. And the next one I really want to talk about is another wearable of those technologies. And I kind of kept focusing on those physical disabilities and kind of adding stuff, mechanical things onto the system or even electrical things onto the system to give some sort of ability back to that person. So this is the Soul Saber, and it was developed with Olivia Logan and Bryce Wiseman in CRT 399 for Dr. LaPointe. And its task was to kind of measure diabetic ulcers because of how dangerous they are to people with diabetes. They often end up in amputation, so people losing their toes, losing their feet, and then even their legs. And this was kind of done by measuring pressure data over the footbed over time. So not just one instance of how much pressure you're putting down, but how much pressure you're putting down over a long period of time. Maybe a full walking gait, so heel toe several times, or a full day. And my task was really to redesign a sensor that was closed source and make it open source so that we could figure out how to actually measure this stuff. And you see what I kind of ended up with was an 81 sensor array grid right there. So the solution actually was a little bit of that grid you saw there, but I actually implemented it by using Velostat, which is a fabric that changes its resistance as you add pressure, and rows of copper tape that were all had different soldering joints on connected to them that would go back to the board. And And we actually had to redesign this halfway through the semester because halfway through at one of our pinups, he basically told us that this was garbage and he didn't like it whatsoever. So he started from scratch, and we wound up actually having a deliverable product at the end. So hats off to myself and my group because I'm very proud of that one. But the sensor itself actually provides a lot of data and stores it on an SD card, which then can be visualized for the doctor. Kind of still staying on that physical disability was the AFT, which I actually designed outside of class for Dr. Lapointe, the ankle flexibility tester. The idea was brought to me with some drawings already and a kind of rudimentary sensor already existing. But my task was to kind of turn this into a portable product that would be easily manufacturable because it's made out of 80/20 and printed parts, and also sturdy. But then the biggest issue that we had was we have to isolate the leg and the foot while measuring the flexibility of the ankles. And we wanted to do this to mechanically measure the flexibility of the ankle so that people with little to no insurance or who have difficulty paying for medical bills can actually have their ankle measured without having CAT scans or MRIs or anything expensive like that. We can do it within office and measure it really quickly and tell what's been torn, what's been damaged, so on and so forth. So what I came up with is I took some of the drawings in, redesigned a lot of them, but also settled on using a vacuum bag that has pellets in it to isolate the foot and the leg. So you actually just suck out the air and those pellets bond together to make a really tight bond, solidify the leg to the plate and the foot to the plate so that the only thing that's moving is the ankle. And I actually figured out how to print all these parts for Dr. Lapointe, set up all of his printers. And at this point right now, we've finished all of the hardware for the AFT and are only working on the software right now for the load cells and how to read that out as kind of visualize the load cell data that comes out of that. And Bitsy board is kind of like another one of those, but I decided to focus more on the mental disability side. So this is what I wanted to challenge myself and stop kind of going towards the physical disability and solving that in some way, but I wanted to kind of mediate a mental disability. So I focused on individuals that were actually nonverbal. So that kind of is a huge array of disabilities, but people that either can't communicate whatsoever or just use grunts and noises to kind of get things across. So I was actually allotted a 1" by 1" PCB in advanced prototyping course and was kind of challenged to design a meaningful interaction. So it had to be as simple as possible and use the space very efficiently. So the solution I came up with is the Bitsy board, which uses Morse code to allow individuals to communicate. They communicate by using the piezo buzzer and the LED to signify dots or dashes and those two buttons. The piezo buzzer is actually programmed to comply with international Morse code standards. And also I've made all 5 of these boards. You wind up with 5 of them when you order them from JLC PCB. And I've soldered all 5 of them up and actually given them to a family that has a nonverbal child. And they currently still use them. I know they've gone through a lot of coin cell batteries, so that's a good thing. So, and lastly, I wanted to talk about my capstone. So my capstone, the all wheelchair which is a name that Zane decided that was a good one, which I think it's all right. It's all right. But I wanted to focus on wheelchair accessibility for college campuses. So something that I saw a lot of day to day, a lot of problems on the day-to-day with. I have a lot of friends at school. Actually, 2 of the main people at Berry College that are wheelchair bound, I am very close friends with. So I knew that this was a real problem. And you can kind of see in the diagram right there how rolling up to a door and using just one hand to wheel the wheel, you actually turn out of the way or turn into the door if you're only using one hand to steer the wheelchair and the other to hold the door. So I decided I really wanted to design for the individual as opposed to designing for the building, because I wanted to prepare the user for the door and not the door for the user, unlike a wheelchair, a door opener, kind of like that with the buttons and everything. So the way I went about this went through several different design alternatives, but decided to stick with the design alternative that locked the wheels together. So kind of like an axle locker, like you would see in any kind of off-road vehicle whatsoever. So this was done by redesigning the wheels. So I actually redesigned the bearings on the wheels, and then a axle shaft that threads through. and the axle shaft that threads on the inside. These also have keyways that bolt onto it, so everything is completely fastened to the axles. And then a little shifting handle, which rides up a little closer to the user than the brake handles that you would normally use to stop the wheelchair. So I prototyped it in PLA, polylactic acid, which is a prototyping material, but I actually wound up printing all of the parts in PETG, which is more of an impact-resistant material that does a lot better with the strain of those axle shafts and couplings, especially the shear force that's on those things, especially with all the weight being pushed through one wheel all the way to the other. Yeah, and put some people in it, especially my family member, because that's who I have right now. And it works fairly well. Did a time test and have seen consistent results of quicker entries into doors using the locker. So where I'm going, I am currently an applications engineer at TC Poly. I've already accepted my job offer and I'm working right now. And TC Poly right now is developing and has developed specialty filaments for 3D printing applications. So right now, some of those filaments are thermally conductive filaments. You can kind of see on our website right there. We develop heat exchangers, cold plates, and battery packs to keep all of those things cool or hot, depending on what your application calls for. But also what I'm working on currently myself is a lot of R&D and then part design and printing. So right now, a lot of the R&D that I'm working on right now is continuous fiber extrusion. That's one of the biggest projects I'm working on. And you can see in the top right corner there, that's a continuous fiber extrusion nozzle. The left chamber right there is the base polymer extruder. And then the two right chambers, one is for the continuous fiber and the other one is for a coating polymer. So the coating polymer goes around the fiber, adheres it to the base polymer, and then adds some sort of ability to your print. People right now are mostly using fiberglass and carbon fiber to add strength, but we're kind of adding other materials that I'm not really allowed to talk about, but to add certain things, certain capabilities to 3D prints that they don't have already. Also, IDEX is another project I'm working on, independent dual extrusion. So you can see right there in the other picture, there's two extruders that are connected to separate stepper motors and move independently of each other. So that is something I'm working on as well as redesigning customer parts for printing to make them printable, and then developing print profiles for all of our new materials so our customers can print them. For right now, what I'm doing is I'm currently 3D printing injection molds for face masks, because our material is actually used in the injection molding industry because of its thermal conductivity. As it's as thermally conductive as aluminum, actually. So you actually 3D print these molds, and they take, I think, about half as long as it takes to mill, and they are, you can just pump them out and have tons and tons. So we've been sending these molds off to some of our customers, and they've been injection molding lots of face masks, like you can see in the top right. Also, I've been printing lots of face shields and ventilator splitters for some of the hospitals we've been partnering with. We've been partnering with Grady, been partnering with Emory Johns Creek, and several other hospitals I can't think of right now. But that's what I'm doing currently. So thank you.
All right. Very good, Andrew. Thank you so much.
Thank you.